Good, so let's move on and talk about free convection or natural convection. So yeah, let me just write this. First of all, people call it both natural and free convection. Means the same thing. All right, so the idea behind natural convection is that in some situations, let's say you have like a wall like this and it's much hotter than the air that's next to it. In that situation, the wall provides heating to the air and there's a gradient in temperature. Wherever there's a gradient in temperature for an ideal gas or something like an ideal gas, you're going to have a change in density. And that change in density means you have a column of air that has a different sort of mass associated with it than an adjacent column of air. And if that's the case, you get this buoyancy-driven flow, right? It's just, I mean, your intuition about like how balloons work or things like that. A hot air balloon, right? That's applicable here. You have this lower density fluid, wants to rise because it basically weighs less as a unit than something that's colder right next to it. So this buoyancy-driven flow can lead to the natural convection currents that maybe we can have a correlation. Sketch what maybe this looks like. So let's say we have some wall over here. So there's some wall, and this wall has a surface temperature. This is Ts, and then out here we have some T infinity, and let's say Ts is greater than T infinity. And it's greater to the degree that it's enough to induce these natural convection currents. So what happens is you get this flow that sort of comes in next to the wall, rises up, and you get a velocity gradient that forms like this. All right, so this is maybe one example. Sorry, my sketch isn't so great, but you get the idea that there's a hot wall, some fluid next to it. This is one example, right? There's other examples of how this type of thing can happen. So let's say you have a hot plate on the bottom and a cold plate on the top. So let me just draw it like this. Let's say that you have, a cold plate up here, and down here we have a hot plate. And they're horizontal, right? But doesn't really matter too much. In this situation, well, what would happen? You'd have, say, maybe air comes in, and it starts to form this sort of updraft type situation. The air goes up, it hits the cool plate, maybe it cools off a little bit, and then it starts circulating down. So you can get these sort of circulating natural convection currents if you have a situation where you have something hot and then a cold thing above it. Right? So think of like the Earth, right? Our atmosphere sort of works this way. What if you had a different situation? So what if you had hot plate on top and cold plate on the bottom? Oops, cold plate on the bottom here. Then what would happen? Would you get a natural convection current in this case? I'm seeing no's, right? Why is that? Well, you have basically fluid wants to come up right next to this plate. It's low density. The more it sits next to the plate, the lower density it gets, the more it wants to rise. And it never wants to do anything other than rise. Right? So just by reversing the geometry, you have now shortcutted or shorted the ability to have a natural convection current. Okay, so keep in mind for natural convection, it's important not just like the temperatures, the geometry that's involved, but also the relationship between surfaces. So now your correlations have to account for this as well. So let's maybe get some parameters in mind or some calculations in mind so you can analyze these things. The first thing is something called characteristic velocity for natural convection. So you're familiar with characteristic velocity from internal flow. Right, that's U bar, or we called it UM sometimes. For external flow, that's U infinity, that's the free stream velocity. For this, we don't really have, like natural convection, the velocity current is developed from the presence of the temperature gradient. So we don't really have like a external velocity that we can just sit there and take, like you're given to us, right? So we have to develop that velocity from the surfaces, from the problem itself. What does that maybe look like? So I'll just give you the correlation here, or relationship. It's U characteristic is equal to the square root of gravity, g, times the length, times beta, which we'll talk about in a second, times ts minus t infinity. All right, so I can compute the characteristic velocity if I know these things. Close parenthesis here. All right, length would be something like the vertical height of the surface that you care about. Gravity is obviously like gravity in the direction of the plate that you're analyzing. And then Ts would be the surface, T infinity the free stream. What about this beta? What is beta? I guess that's kind of an important thing. So beta, here, let me just write this out. So beta is the volumetric thermal expansion coefficient. Volumetric thermal expansion coefficient. If you've had thermal, maybe you recognize this, maybe not. But basically, it's defined as follows. So it's beta is equal to minus 1 over density rho times the partial derivative d rho with respect to temperature when you hold it at constant pressure. Okay, so what this is basically saying, if you can get past the PDE part of this, what it's basically saying is how does temperature affect the density of my fluid? Okay, so maybe to think about this a little bit further, more concretely, we can plug this into like the ideal gas law and think about how that looks. So we could say, okay, P is equal to rho times R times T. If I solve this for rho, I just get rho equals P over RT. So then I can take this equation, rho equals P over RT, and plug that into my definition of beta. And I would get beta is equal to, let's see, minus RT over P times the partial with respect to temperature of P over RT. We've got to this point, and we say minus RT over P times now minus P over RT squared. Okay, and then we can cancel stuff out. So the minus RT minus R1T, and P cancel out, and we're left with beta is equal to 1 over T. Okay, sorry, that was a bit confusing, but all you need to remember from this process is two things. One, beta is derived from the ideal gas law. So if you have an ideal gas, this is the relationship with temperature. If you don't have an ideal gas, you can't use this, right? You have to do something else. The other thing to take away is that beta is just 1 over temperature, so it's the inverse of the absolute temperature in Kelvin. Yeah, question? Okay, so if anybody didn't hear that, what we're doing is when you take the partial derivative of basically 1 over t, that brings a minus out there, and you get minus 1 over t squared. So we evaluated the derivative, we get that extra minus sign and an extra t in the denominator, and then beta is just 1 over t. That's a lot of words just to say that beta is 1 over t, but now you kind of know where it comes from, right? So this is a volumetric expansion coefficient. Ideal gas, you use this, you can just plug it in. For most of the natural convection stuff we care about, I would say you can assume ideal gas, right? If you're starting to get into stuff where there's like viscosity effects or things where there's a compressibility factor, then you want to use maybe a lookup for this value instead of this simple computation. Okay, so we now have beta. We can go back to computing some of the non-dimensional values for buoyancy-driven flow. So let's take our model of characteristic velocity and apply it to the Reynolds number that we've already sort of established. So we have Reynolds number, we have a characteristic length, we have a characteristic velocity. So let's take now our Reynolds number definition and substitute in the characteristic velocity. So rewriting this as just Reynolds is equal to rho L characteristic over mu times this U characteristic, which is the square root of G L beta Ts minus T infinity. Okay. Why did I do this? Well, I just want to have an intermediate step so we can see what's maybe going to be convenient. So it's kind of annoying to have this square root thing in here just when we're talking about non-dimensional parameters. So what people typically do is they just square both sides. And so we'll take this entire equation here and square it. And then what you're left with is Reynolds squared, all that stuff on the right. So let me just write this. Reynolds squared is equal to, simplifying a little, G L characteristic cubed times beta times Ts minus T infinity divided by, so we're going to combine together the density and the viscosity and use the kinematic viscosity nu. All right, so that's the nu squared in the denominator. Okay, so this non-dimensional group, Reynolds squared for the characteristic velocity that we have, is actually given a special name. And that special name is GR, which is the Grashof number. Right? So when people are talking about buoyancy-driven flow, it is the Grashof number that's important, and that's what's referenced. Yeah, so the question was, is there any reason to use beta rather than like the alternate formulation? Yes, so the reason why we use beta is because if you do have an incompressible, an incompressible fluid where, non-ideal fluid, let me say, not incompressible, a non-ideal fluid, where the density change is not just related to the temperature, you can just go look it up in ease or something, right? So I can look up beta, and it will give me back a value that's maybe empirical, not just 1 over T. And then we can just throw it in there and not have to worry about it. Any other questions on this? Okay, so we have the Grashof number. This is how we're going to describe our characteristic sort of relationships. The other thing we can say is that there's also the Rayleigh number. So RA, this is RAYLEIGH. Rayleigh number. The Rayleigh number is the Grashof number times the Prandtl number. So when we start to want to include like the fact that the Prandtl number might not be 1 for a lot of these, like you might have some fluid where the thermal diffusivity is much different from the momentum diffusivity. In those cases, you want to just use the Rayleigh number instead. Right, so you have correlations that are going to be in terms of Rayleigh number, in terms of Grashof number, and they all involve the Prandtl number in some way. Okay, so this is sort of the set of non-dimensional values that we need, and then we can go back and compute the correlations with them. Let's see. So one other maybe minor point to make here. I'm talking about this Ts minus T infinity. So what happens when like Ts is less than T infinity? Does that change things? Like, do I get a negative Reynolds number? Well, not really. I mean, it does change things, but you don't get a negative just because we don't want to deal with that. So instead, what we do is we say, I'm going to just erase, I know you can't necessarily, but I'm going to do this just because I want to write it twice. This would be actually the absolute value. So let's take the absolute value of the temperature difference and define it this way. Okay. All right. So that's how we, that's how we develop things. We also, just as a final note, always use the same Nusselt. So we'd say Nusselt bar is equal to, let's say, H bar times L characteristic over K. So for like a natural convection problem, you might have a L characteristic is like the height of your wall or something. Nusselt bar would be the correlation. H bar would be the dimensional thing you'd want to calculate from that.